All right, thank you very much for the invitation. It's a pleasure to be back here. And I'm really impressed by the abundant supply of Hager-Romo chalk. The general question that I'm thinking about here is if you have so if Y is a three-manifold, V is a vector field in Y. So I've written various papers about periodic orbits of certain vector fields. So you can ask me, does it how many periodic orbits does it have, and so on. But a more refined question you can ask is, what can you say about the dot or link types of periodic orbits of phi or unions of them? Particularly three-dimensional dynamics question. And that's a very vague question. Like you can, and maybe doesn't make very much sense. That you would probably expect that if you change the vector field, it's going to change a lot what knot and link types you have. But you could ask, well, how much is that the case? So how stable are knot and link types? So if I have one vector field, it has particular periodic orbit or set of them, which determines some knot or link type. If I, change the vector field, is that still going to be there, or could it disappear? So when I ask more specifically, how stable are knot or link types of periodic orbits under changing the vector field? So that's still way too vague. So I'm going to specialize to a particular kind of vector field. So the particular case I'll talk about today is you have sigma is a symplectic two-manifold or a surface with an area form. And phi is an area preserving diffeomorphism of sigma. And the standing assumptions I'll make which can be weakened somewhat, but just to make it easier to give the basic idea, I'll assume that phi is non-degenerate. So all the periodic orbits are non-degenerate in the sense which I'll review in a minute. And the surface is allowed to have boundary. So sigma is a compact surface, may have boundary. If it does have boundary, then I'm going to assume that phi sends each boundary component to itself. And I'll assume that near each component of the boundary, there's a neighborhood which is identified with minus epsilon 0 across a circle. And for me, a circle is R mod C. So this is the neighborhood of the boundary where 0 crosses 1 is the boundary component, in which, well, and there exists an irrational number theta such that if these coordinates are, say, x and y, then phi xy equals x comma y plus theta. So it's just an irrational rotation in your boundary component. You can probably weaken this a lot, but this makes it easier to do things. So given any diffeomorphism of a surface, you can make the mapping torus y phi. So this is the interval from 0 to 1 cross sigma modulo an equivalence relation where 1 comma z is equivalent to 0 comma phi of z. So this is a three-manifold which fibers over S1, which is the interval with the ends identified with fiber sigma. And if I denote the coordinate on this S1 by t, then this has a canonical vector field which I denote by dt. So this just increases this coordinate, or more precisely, it increases the 0, 1 coordinate here without changing the sigma coordinate. So the picture is I draw the whole thing around a circle like this. So this is sigma. And I started at point Z, and I follow this vector field around for time 1, and I come back to phi of Z. So periodic orbit with the map with period k. So that's just a cycle with k points that are permuted by phi. These correspond to periodic orbits of the vector field, such that the projection to S1 has degree k. So this is the particular three-dimensional vector field I'll talk about today. I should mention there's also a very similar story for contact three-manifolds and Reeb vector fields, but I don't know, and there's an analog to the theorem I'll state, but I don't know how to prove it. I don't know if it's true. Okay, so in this context, we can ask, well, what are the not or link types of periodic orbits? And we can be a little more specific because this vector field is transverse to the fibers of this fiber bundle. So we can just look at knots and links that are transverse. So we'll define a braid.
How come that phi of Z and Z are not matching, even though that's the mapping torus?
Sorry, say it again.
In the mapping torus, aren't we identifying the Z and the phi of Z? So
Yeah.
how is it not matching?
So one of them's like 0 cross Z, and one of them's like
Oh, that was,
0 cross
it's
B,
one.
0 cross B of Z.
So to be a little more precise, I should have said that this here, this is 0 cross C. So I think here, this is really the point 0, comma Z.
Oh, and that's also 0, phi of Z. Okay.
But when I follow
I get
the
it.
vector field around, it comes up to 0, comma phi of Z, because that's the same as 1, comma Z. Other questions? So the braid in Y phi is an oriented link. In Y phi, which is positively transverse to the fibers. And we're interested in these modulo isotopy. So an isotopy of braids. This is a smooth one parameter family effect. And in classical knot theory, well, you might have seen braids as looking like this. So these are elements of a disk across an interval. But if you sort of wrap around the interval, so in the case, you can sort of close these up to get things that look like this. I don't know what I did. Well, this is not the closing up of what I just drew. Anyway, you can, never mind. This is why I'm not a topologist. Anyway, you can close these up. So in the case where sigma is the two disk, these are braids in a solid torus, and these are what are called closed braids in knot theory. But you can just as well look at braids in a general mapping torus. So then the question I want to consider, so what can we say about stability of braid types of periodic orbits or unions of periodic orbits? Of this vector field dt on the mapping torus. So any periodic orbit of dt gives, or any union of them gives you a braid in the mapping torus. And then if I say stability, well, it means I want to change the map phi. How do I want to change the map phi? I want to do it by Hamiltonian isotopy. So the cool way to talk about Hamiltonian isotopy, which I learned from Oliver Edmeyer, is you take a function h on the mapping torus. This is going to determine an isotopy of the map phi. So to start, we can pull it back to map h tilde from 0, 1 cross sigma to r. Or the quotient map that defines the mapping torus. And let's define ht from sigma to R by HT of Z equals H tilde of TZ for T from 0 to 1. And I'm going to assume, to avoid trouble with my boundary conditions, that HT is constant near each component of the boundary of sigma. And I have a Hamiltonian vector field xt defined by omega of xt dot equals dht. I know there's some religious dispute about the sign of this equation, so I apologize if I offended anybody with this sign. Then we've let t goes from 0 to 1 to be the flow of xht. And I define phi h equals phi composed with r phi 1. So this is a, so I started with phi, I've applied this isotopy, I've gotten phi h.
Why did you start with the H on the mapping torus and not just on?
Yeah, so you could just do an H on 0, 1 cross sigma. So you'll see, I think you'll see in a minute why I want to do this way. So basically you have to worry a little bit about what happens at 0 and 1, and this is a way to avoid worrying about it. Observe, there's a diffeomorphism F from the mapping torus of phi to the mapping torus of phi h, as defined by f of t comma z equals t comma bar phi t inverse of c for t from 0 to 1. So you can check that that works, that this is well defined with respect to the equivalence relation that defines these mapping tori. If I just define my Hamiltonian 0, 1 cross sigma, then I would have to be careful about t equals 0 and t equals 1 to make sure this is smooth there. Okay, so then we can ask the question. So how do braid types of periodic orbits in y phi relate to braid types of periodic orbits in y phi h. And then to say a little more about this, so let's define Hofer norm. I'm putting this in quotes because I'm not defining it. I'm defining it a slightly non-standard way, but it gives an equivalent result for defining the Hofer distance. So defining norm of H is just the max over y of H over y of H. So this is some measure of how big a change you've made to that phi. Now I can say the theorem. So under the above assumptions, so remember I assumed that phi is non-degenerate. It has these boundary conditions. So let's assume that phi h is also non-degenerate. Phi h will still satisfy the boundary conditions because assume that ht is constant near each boundary component, which implies the isotopy does not move at all near the boundary of sigma. So let alpha be a finite set of simple periodic orbits. Of dt, or equivalently periodic orbits of phi. And simple means that I don't sort of go around the same circle multiple times. And actually, I put my assumptions in the wrong order. Sorry. I'll fix it in a second. So then there exists delta greater than 0. I can actually give you an explicit bound on how small delta has to be, such that H from y phi to r is as above. And I should have put this down here. Sorry. Go to copy paste to my talk. So if H is as above and if phi h is non-degenerate, and if the Hofer norm of H is less than delta, then there exists a union, just a finite set theta of simple periodic orbits of phi h. Such that f of alpha is isotopic to beta. So In short, if I start with my union of periodic orbits, I make a modification of phi, which is sufficiently small in the Hofer norm, then I have an isotopic braid of periodic orbits. I have to start with the set of orbits first, and then I get the delta.
So is there any statement you would expect for non-Hamiltonian isotopies?
That's a great question.
Well, I think you can break it for the torus in a silly way, as in you take a rational torus rotation, you make a tiny Hamiltonian perturbation, then you can change the rotation number of the rational part to, you know, irrational Diophantine rotations or something. And so you get some kind of approximation by maps with.
Yeah. Yeah.
So for the contact version, so it would be like you replace the Hofer norm with the C0 difference of the contact forms, and then with the braid type be something like the transverse link type. Is that
exactly?
Okay. So then and will it be kind of clear from like the proof you're about to do that like why it doesn't work or why it's more complicated?
Yeah, I hope so.
Okay, great.
Very good. So you made a couple of my remarks for me, so I don't have to.
Sorry.
That's fine. So here's some other remarks. So first of all, this generalizes office, manifest, which is in their most recent preprint on the archive. So their theorem proved a similar statement, but they were assuming that phi is a Hamiltonian isotopic to the identity, and that the periodic orbits in alpha are actually coming from fixed points of phi. And this question wasn't really on my radar screen until I learned about their work, and then I realized that with some things that I knew I could generalize. Yeah.
So, do you have any sense of to what extent this fails if you sort of drop the homogeneity in alpha, or if you try to impose some homogeneity in alpha? In that, like delta potentially gets, as you choose basically more and more complicated braids, or maybe thinking simply just fixed points of larger iterates, delta might go to 0. Because delta is dependent on alpha. Do you have any sense of whether there's like any chance of there being a global lower bound that's independent of the sort of iteration number, or alternatively at this point that choice?
So I think my method of proof won't show that, but that it could still be something you can say. So
this is sort of, I mean, just intuitively, it was a very different flavor of the question, but this one is more about like cancellation of point. You're trying to like show a non-cancellation condition for individual pairs as opposed to.
right, that's right.
Right. Thank you. Sorry.
Sure. Okay, anyway, so this is heavily inspired by the work of Alvis and Vibus. I'll remark that I'm not allowed to say the word obvious, but it's sort of obvious in quotes. For C0 small perturbations of phi. Because if I have a periodic orbit of phi, which is non-degenerate, well, locally it corresponds to an intersection of in sigma cross sigma of the diagonal with the graph of phi to some power. So it's periodic. orbit of phi to the k, some intersection. And the non-degeneracy condition implies that if you, instead of looking at the periodic point, you apply the map to a little circle around the periodic point, you get a circle in segment cross segment, which actually has linking number plus or minus 1 with a diagonal. So if you do a C0 small deformation of the map, that circle will still have a non-zero linking number with a diagonal, so there have to be an intersection. So you'll still have a periodic orbit, which will give you an isotopic braid. So this would not be a very impressive theorem if instead of saying that the Hofer norm of H is less than delta, I said that the C0 norm of H is less than delta. However, this theorem is not obvious because the map phi H, its definition depends on the derivatives of H and not just the C0 norm of H. So the Hofer norm doesn't give me any control, or at least not obviously, over the C0 norm of H. So that's why this is a sort of a non-obvious kind of stability.
Question. You can't just shift H by a constant so that this norm is comparable to the C0 norm?
And when he says C0 is like the Hamiltonian.
Of the map versus the.
Sorry, right, that I misspoke, yeah. C0 norm of H is small is what I'm saying. I'm sorry. It's a C0 norm. What's obvious is if the C0 distance between phi and phi H is small. What's not obvious is if the C0 norm of H is small. Sorry,
I misunderstood.
I said the wrong thing, as I often do. And as well, Julian said this, but I'll write it down just in case anybody missed it. So the question, analogous statement for contact three manifolds, I don't know the answer. But you let Y3 lambda be non-degenerate contact three manifold. And let alpha be a finite set of simple braid orbits. Does there exist some delta greater than 0 such that if f is a function of y with C0 norm less than delta, if f is this, and if e to the f lambda is non-degenerate, then there exists a finite set beta of simple braid orbits of e to the f lambda, which is isotopic to alpha. Through transverse links. So this is very much analogous to the theorem. I don't know how to prove it. There's a couple of technical things which you'll see that come up. I didn't try super hard to fix it, so maybe next week it'll be solved. But anyway, it's a question right now. All right, so any more questions about the statement before we start talking about how to prove it? So the proof. So it uses holomorphic curves. But I'm not going to talk about any kind of floor theory. For this particular problem, talking about floor theory seems to be a distraction. And so I'm just going to talk more directly about the holomorphic curves that I need. So to start, so we let J of phi so let this almost complex structures J on R cross Y phi such that J's are invariant. Did I break something? I made a concerning sound. Oh, okay. So J sends the vertical tangent bundle E of the mapping torus to itself, rotating positively with respect to omega. And J sends the derivative of the R direction, which I denote by S, to dt. So these are the kinds of almost complex structures that you would consider in order to study the floor theory for symplectomorphisms or the periodic floor homology. And so sorry. All right, to next definition, an orbit set is a finite set of pairs alpha mi where the alpha I are distinct simple periodic orbits of phi. And the mi are positive integers. We'll say alpha is simple if mi equals 1 for all I. So it's just a finite set of simple Reeb orbits. And also in general, an orbit set has a homology class, which is sum over I of mi times homology class of alpha I in H1 of Y phi. Okay, so if beta is another orbit set, to be equal to alpha if you want. So it's like the homology class of alpha is the homology class of beta. To the y phi beta. This is some standard, well, commonly used stuff from ECH and stuff like that. So this is the set of two chains Z and Y phi with the boundary of Z equals alpha minus beta modulo boundaries of three chains. So this thing is a affine space over H2 of the mapping torus. And then I define MJ. But if I have J, alpha, beta, and Z as in those definitions, this is the modular space of J holomorphic currents C in R cross Y asymptotic to alpha as S goes to plus infinity and to beta as S goes to minus infinity. So like currents, I'm not doing any fancy analysis here. I just mean you have a finite set of holomorphic curves in the usual sense. Each one has a positive integer multiplicity. So you can think of that whole thing as some chain. And it's, well, you can intersect it with a slice of some number of times y cross y, and that it limits to alpha as S goes to plus infinity, and to beta as S goes to minus infinity as a current. So these are the usual things that one studies in the ECH and so on. So some key facts about these that we'll need. So first of all, I forgot to add the assumption. I didn't say where the Z comes in. So then I want to assume that the relative homology class of C is equal to C. So if MJ of alpha beta Z is not empty, then the action difference integral over Z of alpha, let me write it over here. The integral over Z of omega is greater than or equal to 0 with equality only if alpha equals beta and Z equals 0 and C is R plus alpha. So I'd like to, in the arguments to come, I'd like to talk about symplectic action, but there's no, in this situation, there isn't really a well-defined definition of the symplectic action of a periodic orbit. I can talk about the action difference between two unions of periodic orbits, and that's not even well-defined. But if I choose this this relative homology class Z, then it's finally actually defined. I just integrate omega over Z. So this inequality, it follows from the definition of J, because J, these conditions imply that at each point of a holomorphic curve, omega is pointwise non-negative, and it's zero at a point only when the tangent space of the holomorphic curve is spanned by ds and dt. So that's the first key fact. And the second key fact is that if modular space is not empty, then the ECH index is greater than or equals 0. I don't have time to review the ECH index, but it's a topological quantity. It's an integer which gives an upper bound on the Fresnel index of holomorphic curves. So the ECH index is greater than or equal to 0. So this is true. I have to assume if J is generic, and the moduli space is not empty, then the ECH index is greater than or equal to 0. Equality again, same case as before. And the third thing, that if J is generic, and if I have a current C in this moduli space, if this has no multiply covered components, so remember that C, this is as a current, this is a sum of holomorphic curves with positive integer multiplicities. No multiply covered components means all those multiplicities are 1. Then the Fresnel index in the C is less than or equal to the ECH index. I of C with equality only if C satisfies the ECH partition conditions. And what are these partition conditions? So we actually need this. The partitions really matter for this theorem. So let's say this orbit's at alpha, so alpha I mi.
Can you say like colloquially why you'll get that the ECH partition conditions are satisfied? Like heuristically, before you write down the partition conditions, like why?
Why it's true?
Yeah, not like the equality of the ECH.
You want me to tell you why you get the ECH partition conditions?
Yeah, like how do you get them so that you know that you can prove your theorem?
Well, so there are two different questions. So one question is, how do I prove that equality applies to partition conditions? And that's a complicated one. And then the other question is, why do the partition conditions, being what they are, lead to the proof of my theorem? That's I can answer more simply. So that's what I hope to manage to explain. Yes.
Just a quick, so generic means more generic than the usual generic, right? Like this is like so meaning that like, you know, it's not, you're not just assuming transversality with J, you're assuming like more than that. Is that
No, it's
right?
basically just transversality. And I should say that I lied a little bit. I should also say, there's some little fine print here,
Okay.
which is that also C has no fibers. So the conditions on J imply that the fibers of the projection R cross Y feed R cross S1 are holomorphic. And when sigma is not a sphere, those are never cut out transversely, so that's bad. So it's not going to cause too much trouble what I'm about to do. So let me just tell you one of these partition conditions, because I think am I supposed to finish at 5 o'clock sharp?
Yeah, but you can take it.
Okay, so I'll try to wrap this up here. I have a lot to say, not much time. All right, so if alpha I is positive hyperbolic, and positive hyperbolic means that the linearized return map of the flow around alpha I has positive real eigenvalues, then C has mi positive ends at alpha I. So in general, like C could have a single end asymptotic to the mi-fold cover of alpha I, or the multiplicities, the covering multiplicities of the covers of alpha I at which C is positive ends. That's a partition of the integer mi. And in this case, the partition is just 1, 1, 1, 1, 1. Sorry?
This is one of the conditions in the ECH partition condition.
That's right. So examples, partition conditions that are relevant to what I'm about to do. If alpha I is negative hyperbolic, then well, the partition is negative hyperbolic means the linearized return map has negative real eigenvalues. And the partition is 2 with mi is even, and 2 1 with mi is odd. So that means when mi is even, this holomorphic curve has mi over 2 ends that are asymptotic to covers of alpha I, each of which is a double cover of alpha I. And then for elliptic orbits, to the lack of time, I'll tell you what it is, but it's more complicated. And different for positive versus negative ends. So that's enough background. 5 minutes left. What's the proof? So I'll give you the crash summary of the proof. So first of all, there's if I have H1 and H2 are two Hamiltonians, or let's say H minus and H plus, from Y to R, and if H1, H minus is everywhere less than H plus, then I can look at the set of S comma Y in R cross Y phi, such that H minus of Y is less than or equal to S, is less than or equal to H plus of Y. Picture is so this is S. This whole thing is R cross Y phi. So looking at the graph of H minus in here, and the graph of H plus. Let's call this whole thing W of H plus H minus. So W H plus H minus is this region in here. And the idea is that in a certain sense, which I won't explain right now, this is a symplectic cobordism between the mapping torus of H plus and the mapping torus of H minus. H minus. So this graph of H plus is equivalent in a certain sense to Y phi H plus. And this thing corresponds to Y phi H minus. So I have a cobordism between these two mapping tori. And there's a similar story for everything I told you about holomorphic curves in R cross Y phi. There's a similar story for holomorphic curves in this cobordism with a suitable completion of the boundary. So what we do to prove the theorem so suppose I have a Hamiltonian, which is between zero, everywhere between 0 and some constant C. So I now look at a composite cobordism. So this is the graph of H equals 0, which is Y phi. This is the graph of the constant function C, which is, well, it's Y cross the mapping torus of phi, where with the constant Hamiltonian C, the constant Hamiltonian doesn't do anything, so it's also Y phi. And then in the middle, I have Y phi H. And then I have my collection of periodic orbits alpha up here, and my collection of periodic orbits alpha over here. And I look at holomorphic curves in this cobordism. For holomorphic currents. From alpha to alpha in the homology class 0. cylinders, which have zero, that are unions of cylinders with no multiply covered components. So if I start with this sort of trivial morphism, then there's only one element of this moduli space, which is this union of trivial cylinders. I now do a neck stretching along VH. So I stretch the neck along VH. And, when I stretch the neck, I have alpha over here, alpha down here. When I stretch the neck, these unions of cylinders are going to break into something. That's going to be beta. So beta is some orbit set, beta j and j. And if this is a simple orbit set, so if all these nj's are one, then that's the braid I wanted. So something I forgot to say in the equality conditions for the ECH inequality is that C is embedded. So the cylinders you get here are actually embedded in R cross Y phi, and you can check that they give an isotopy. So if beta is simple, and then if beta is not simple, the partition conditions imply that the number of ways to glue is even. So I start with this trivial moduli space, which has just one element. I stretch the neck, and it's going to break into an odd number of things. And the things for which beta is not simple, there are an even number of such breakings. So it has to be at least one breaking where beta is simple. And that's the proof. Sorry for going over time. Thank you.
The key use of the partition thing, of the ECH stuff, is just to make sure that the intermediate thing is not multiply covered. Like
That's the most important part, yes.
okay, or one key, I guess one key place. So like if you try to replicate the proof with just doing regular SFT neck stretching of the trivial cylinders, that's the thing that you would have trouble dealing with without the.
Right. So basically I'm doing some kind of intersection theory to analyze these holomorphic curves and how they can break.
Where's the delta bound?
Right. So I didn't have time to explain this, but when you do this neck stretching, in general, worse things can happen. So in general, you're not just going to get a two-level building, but you can have additional levels. You can have some levels in the Y, well, have some additional levels in each of these three symplectizations. If you choose delta small enough, then so that you can sandwich at H at between 0 and C, where C is delta, then you don't have enough action for anything bad to happen down here or up there. And here, you have no control over what's happening in here. But the ECH index tells you that you don't have enough index for anything bad to happen in the middle.
Oh.
So there's not enough, if delta is small, there's not enough action for anything bad to happen on the end. And then in general, there's not enough index for anything bad to happen in the middle. Yes?
So if you have this Hamiltonian case, because the general contact case, then there's like iterate of the, if you have, you can ask, like if you have a set of periodic points, all of which are of the same iterate, do you show that there's a corresponding set of the same, I guess there is a topic, that there are also fixed points of the same iterate of the Hamiltonian? Like if you said that if you have you have this vector field, you look at a periodic point, you look at a periodic orbit of it, these naturally are associated, so connected components of that are naturally associated with the iterate of the Hamiltonian diffeomorphism.
Yeah.
So you can ask for a closed orbit, which is sum of orbits, all of this, sum of periodic corresponds to some of periodic points of the same iterate of the Hamiltonian diffeomorphism. So it's a slightly refined question, which is like, not just the braid type is the, maybe we just ask it later, I guess, I'm not sure.
I mean, you can also look at braid types as iterates of, phi to the sort of least common multiple of periods. I think he's kind of.
And do you show that there's still one of the same?
Yeah, I think the argument implies that those are isotopic too. I think you kind of lose information when you do that.
What?
I think you lose a little information when you do that. Like I think there's a injective map from braid types for phi to braid types for phi to the k.
This is like I was trying to understand the sort of use of ECH here. This whole argument is almost like a spectral invariant argument, but you kind of using ECH to get embeddedness of this sort of continuation map curve, effectively, which basically higher dimensions is automatic, and at this dimension is you have to do more work for it.
Yeah, so the ECH does give us the embeddedness, and I think what's a little more crucial is the partition conditions. Shows we get a simple orbit set.
Okay.
And yeah, the paper by Alves and Maives, they wrote this in terms of filtered Hamiltonian phenomenology. So of course, I found that for this more general situation, it wasn't helpful for me to try to talk about filtered PFH.
Okay, so since we went a little over time, maybe we can take the speaker again and more questions afterwards.